Hello comrades, my name is Fritz and welcome back to Kerbal's space program, New Horizons. It's been a while, but we're back, we are back indeed. And in today's episode, our very own Jebediah Kerbin, just in time for Christmas, is getting a brand new comsat system. So without further ado, 5, 4, 3, 2, 1. Ignition sequence start. We have liftoff. Coming up now on first stage separation. This is usually the moment where everything goes wrong. Hopefully these separatrons will actually separate. Here we go, and they worked perfectly, first time. That was unexpected. Usually you see them flying off the sides of our external tanks and the main rocket's actually colliding with the central motor and then the whole rocket falling out of the damn sky. But yeah, luckily for us that worked beautifully, absolutely flawlessly, and I'm genuinely surprised by that. Our spacecraft is going up straight as an arrow. We are just about on at the 90. I've pitched the spacecraft slightly askew because our velocity vector wasn't quite following us in the early stages of the launch, but that should have cleared itself up by now, and indeed it has. We are pretty much perfectly on the straight and narrow. Veering a couple of degrees left and right, that shouldn't pose too much of an issue now. Yeah, we are going way too high for our own good. I haven't been paying attention at all. Waiting for this stage to go. This stage will go with quite a bang, so hold on to your hats, ladies and gentlemen, because I've fitted this with a trifecta of these huge big booster ullage motors, so this should go off with a bit of a pop, not too much, but yeah, hopefully we should get some nice screenshots of that. Nice one there, actually. That's always very good. And you can see we've got a much more expanded collection of satellite technology going on our spacecraft as we cut back for the scenic mode, hitting space and waiting for the engines to go. Off they pop, and those two engines igniting perfectly on cue as we hurtle into the upper atmosphere. This stage doesn't have quite so much delta V as the stage before it, but we should be making good progress into space. Now the key difference with this current comsat system is that we are using 4 instead of 3 satellites, which means we need a phasing angle of about 90 degrees, as close to 90 as we could possibly get. Now, our previous satellite system had a phasing angle of 120 degrees to get full coverage of our 360 degree orbit, of course. So, what we're going to do is inject ourselves into a nice, low, fast orbit, burn up to an altitude that's perfect for a geosynchronous or geostationary orbit. Geostationary orbit and geosynchronous are two slightly different things. One is a subset of the other. A geosynchronous orbit is one that rotates with the same period as the parent planet. A geostationary orbit rotates at the same period over the equator. That's the key defining feature of a geostationary orbit. Idea first devised by writer and kind of amateur scientist Arthur C. Clarke, famous for writing the 2001 Space Odyssey series. I've been listening to far too much David Bowie for my own good. Actually, that album, Space Odyssey, or David Bowie 2 as it was called in 1969, does have some hidden gems on it besides the main hit single from that year. I thoroughly recommend that. Right, we are pushing out perhaps up a bit too much for my own comfort here. We're going to right up, right against it, and then kick it up to full thrust once again. Doing quite well on this little engine. We're about to eject our nose cone here using our RCS thrusters. well, that nose cone contains some RCS thrusters. We're going to use the separatrons. Off goes the nose cone, like so, and then decouple and fire the vector engine. Is that what it's called? The Maverick 1D. Ooh, it's another twin nozzle one. Okay, we are sacrificing kind of fuel efficiency here. Yeah, right, that's fine. Okay. Whoa, okay, yeah, we're moving up way too fast. Well, I guess once I've done some tweaking, I will see you when we're ready to start explaining some maths to you. Don't be scared, I've condensed this down into a light-hearted romp into beginner's physics. Okay, I'll see you then. Okay, we're back, and I have boosted the spacecraft into what should be the correct altitude for geostationary orbit. Now, that's only if my calculations are correct. The big caveat is if my calculations are correct. And they do seem quite reasonable, because although we are a bit further away from our apoapsis at the moment, you can see that for our previous satellite the trail is still showing, and that apoapsis is dead in between the three trails of our satellites from yesteryear, shall we say. Now, bit of beginner-friendly physics here. If we consider the forces acting on the spacecraft when it is in orbit, we know that it's the force of gravity acting towards the Earth on a kind of axis, maybe going perpendicular to the spacecraft and straight towards the centre of the Earth, the centre of mass of the Earth. And that force is described by Newton's law of gravitation, Gmm over r squared, the 1 over r squared relationship, which means that it varies with the value 1 over r squared as you travel further and further away from the Earth. Lots of physics relationships actually are described by the 1 over r squared method. So if you double your distance away from a planet, you quarter the gravitational force. That's the 1 over r squared relationship in action. Now, when a body is moving in a circle, it has a centripetal acceleration towards the surface. Now, in the case of a spacecraft in an orbit, the centripetal acceleration happens to be the same magnitude as Newton's gravitational attraction, which, for astrophysicists, is actually incredibly convenient. Because what we can say, I'm narrating this blind here, I will put some calculations up on the screen if possible. What we can say is that Fg, our Newton's law of gravitation, which is described, as I mentioned before, by Gmm over r squared, is equal to the centripetal acceleration, which is described as mv squared upon r. So, the gravitational attraction is equal to the centripetal acceleration of the body towards the centre of the Earth, or in this case, the planet Kerbin. Now, the fun thing about these calculations is that all of this can take place independent of the mass of the spacecraft. So no matter what the mass is, for any main body, it depends obviously on the mass of the body, the parent body, but not on the mass of your object, which is very convenient, and it all works out quite nicely. So what we have is Gmm over r squared is equal to mv squared upon r. Now we know, I will tell you for a start, for free, that v equals 2 pi r over t. That's basic speed is distance over time. So 2 pi r over t describes the speed at which we are travelling around the planet Kerbin. Now, the equation for centripetal acceleration is mv squared upon r, and we have an expression for v, which is 2 pi r over t. And now we can square that expression to give ourselves 4 pi squared r squared over t squared, which gives us overall a value for v squared, which means we can substitute that into our kind of equation, our two equations that we equated earlier, which would then give us, quite a nice view up here by the way, which would then give us the following: Gmm over r squared equals m 4 pi r squared over t squared r. Now the r's will cancel, so you'll then be left with a couple of other intermediate stages, and then once you've cancelled the m's, which appear on both sides of the equation, since m1 is the value of the mass of the Earth, and m2 is the value of our spaceship, m2 features on both sides of the equation, so they cancel quite nicely. And what you end up with, once you've done some rearranging and you've isolated R on its own, you end up with the cube root of t squared gm1, which is the mass of Kerbin, over 4 pi squared. Now, you have to factor in that that doesn't include, that is the distance of us from the centre of mass. Now, our actual distance above sea level is that big cube rooted calculation minus the radius of the planet, which is 600 kilometers, or 600 times 10 to the 3 meters, so we're doing everything in standard units, which would come out to be this value here on our map view, and that of course seems reasonable. And after all that explanation, we should almost be ready to get to our apparatus. So yeah, I'll put that up on the screen in post. So you should be able to follow that along quite nicely. It sounds very complicated with me explaining it, however it's not, I assure you. So it's a very back of the napkin type thing. In fact, I quite literally did it on the back of a napkin. So yeah, that should be good for you guys if you're interested. Okay, we're back, and I gotta say, that was a pretty tense few moments of very finger-light manoeuvring going on, but now comes the moment of truth, because I have no idea whether we have enough electric charge to sustain our numerous comsats. So, here goes nothing, I guess. Yeah, I'm gonna quick save here. Okay, we're back, and we are about to release our final comsat. So, without further ado, I guess we should begin to cast this thing adrift. Now, I didn't want to let you sit through the deployment of all the other three, because it was essentially a very boring and repetitive process. Lots of fiddling that needed to be done. So yeah, we are now carrying these signals, looking fancier than ever. Apologies for the slight amount of background noise. We've got some movement going on in the house, unfortunately. I do like to pretend to get up early and then just walk around and pretend I'm the only one alive. Maybe that's just me, but in any case, yeah, that is happening. As we also say, once again, Tumnard Kerbin, on his 2-week mission to deploy these comsats, is doing quite well, and if we switch to the map view, you can see that signals are being carried. I did have a small amount of wonkiness with our second satellite, sorry, no, yes, our second satellite. I was using my hands to kind of line up the phasing angle, and I got that slightly wrong, but yeah, doing things on the cheap here in the New Horizons gameplay mode. And yeah, the solar panels are extended, so we are generating power. I've targeted some of the dishes onto the previous probe, so hopefully we should get a big downlink into a kind of cyclic square, so inscribed into this circular orbit. We have a kind of square with one link going into mission control from the first comsat. Now, speaking of circular orbits, as you can see, our apoapses and paraapses are kind of jittering, and if you look at the numbers in the top left, our values, they are precisely the same, well, to 1 decimal place at least. So we are getting a bit of a floating point precision error, but that shouldn't affect our geostationary orbit too much. So, for the final time, we are going to bid goodbye to this little comsat here. I've transferred some of the fuel from this KW rocketry tank across, because, well, we're using the Oscar B tank within the chassis of this probe, and these 4 tiny ant engines from Rockomax, so the fuel efficiency is going to be fairly good. Thrust to weight ratio not bad either, so we don't really need that much fuel. In any case, what we're going to do is undock from our... where's the thing gone? Decouple from our deployment spacecraft, like so. Switch over. Activate our 4 engines. Oh, we don't have a downlink. Well, this is problems. Damn it. Okay, well, that's an issue. Okay, well, what we can do is hopefully rename the vessel and then see if we can regain a signal from there. Give me a moment, I will be right back. And Bob's your uncle, we had a brief scare where I decoupled from the ship and then the name of the spacecraft obviously changed to a probe setup, so I had to reconfigure the signal, bounce it off the second dish, and then make sure that everything was connected. Now, we might be able to go ahead and link up to our first probe, which is over here. So let's see if we can't go ahead and do that. I'm not sure if we have enough dishes left now, so this could be interesting. Probe 1, System 2. We're going to have to talk to probe 3, that's connected nicely, and then we have one spare dish on this probe. So if we switch to our first probe, using, I think, the final dish on this one, so yeah, slightly redundant there, it looks like. But we might not have to bounce the signal, any further signals off this one. We can use one of the other probes with a spare dish, so that's not all bad at all. Yeah, we've actually got a connection going on here. So it seems we can't view the whole network, but we do have a good kind of system in geostationary orbit around Kerbin. What I do briefly want to do is check that we can get a downlink between these two, and hopefully that will then complete our little mission. Yeah, that's looking good, and we can bid goodbye to our space probe. Doesn't really matter where we come down now, as long as we get back home, and we should indeed have enough delta V to do such things as these. Oh, my computer wants to restart. No can do, buddy. Right, I'm going to warp around to the dark side, just so we can see some stuff on the landing. Hopefully the power systems all stay up and running. That would be handy if the power systems all stayed up and running. As we point retrograde and just burn back to Kerbin. Now, I probably won't burn all the way back to the surface. I will certainly try and get a bit of an aero capture going on, just so we're not kind of hurtling all the way down into the atmosphere. G-force is building up. Hopefully we make it down without running out of fuel. And yeah, looking quite nice after a successful mission. At least I really hope it's a successful mission. I don't want to find that the whole thing collapses the moment we return to Kerbin. 100 kilometers, yeah, we are coming home now. Bring that back to about 25. Yeah, the spool down is, and there it is, our deorbit burn. 1.5 kilometers per second, and we might just make it onto the desert surface here. And heating up quite nicely. The capsule is quite a blaze of glory from the inside. Tom Nard keeping his cool. Yep, he's still happy indeed. That's a lot of benzodrine he's been taking, trying to stay awake on the long mission in geosynchronous orbit. Dropping below the 1 kilometer per second mark, the re-entry heating effect starting to disappear now. I might try and burn retrograde. The G-force is climbing up to about, oh, what's that, 6 or 7 Gs? Not too bad. That's about the amount that your average fighter pilot tends to experience. And looking good. The spacecraft slewing out of control here. Not entirely sure what I can do about that, although, yeah, am I actually using my manual control system? I can point the probe in the right direction. And it looks like we are in for a vertical drop back to the surface. We are go for main chute deployment, and nothing happened. And there we go, so that's a bit scary. 120 meters per second, coming down nice and gently onto the desert surface. There go the chutes, 12 meters per second. We might end up tipping over on landing, but yeah, hopefully it's not too much of an issue. Yeah, maybe landing on water might have been a better option. In any case, we should be in for a fairly smooth landing as we take a look at this rather skew-whiff view outside of the capsule, well, through the inside window of the capsule. Can't see a shadow just yet. I don't believe we've done a desert landing actually, although we might have done one in our very first KSP series. Back in 2014, we came from the moon and we kind of passed over a desert mountain, then landed in a rather sandy little area, 10 meters per second, and looking good now. Gonna use the engine a bit here. 6, and yeah. Crabbing our way down to the surface. 3 meters per second, and there it is. As we out. Tip right over. Well, that's it. Mission end. And yeah, we won't have got any science from it. Actually, we might have done. We've got some. I did some extraterrestrial science by getting Tom Nard out of the capsule. But yeah, let's head back to mission control and see what's what. Well, it's not much, but every little science tends to help. 19.5 science earned on this mission. So yeah, that's pretty good. And we've got all this stuff back from 3,300,000. So slightly less than we started out with before we headed out on the mission. 580 kilometers from Kerbal Space Center, so the value has dropped a little. Anyway, that concludes our second comsat conundrum episode, if you will. Stay tuned for the next episode of New Horizons, where we've got a very important mission. It's Operation Jeb Rescue.